Hey everyone, welcome to this webinar with Trivector Printing. Today I'd like to talk about design considerations for additive manufacturing and particularly FDM or fused deposition modeling. So before we get into the material that we're going to cover on this webinar, I just want to introduce myself. I'm Brandon Hauser, CEO of Trivector Printing. You can see my email and contact information there. I have a great deal of experience in additive manufacturing and also CAD design as well. And before that, I gained a huge amount of experience doing maintenance on aircraft. So not only do I have experience in designing, manufacturing the parts, I also have experience with dealing with end-use parts and maintenance of those parts. So with that said, let's get into the topics that we're going to talk about today. This is basically just a general overview. We're not going to get too in-depth into anything. I'm not going to read off all the topics. You can see them there on the screen. We'll talk about first what FDM is and how it works. And then we'll get into sort of the ways of thinking when you're designing for any type of 3D printing, really. And some of the more specific stuff. Alright, so how does FDM work? FDM is basically, it's probably one of the more simpler 3D printing processes. Basically involves an extruder. In the picture you can see the extruder right here, and you have filament. The filament feeds through the extruder. The extruder heats up the filament, which is a thermoplastic, and the extruder will extrude the filament into a layer, and the part is built up layer by layer. And after each layer prints, the build platform will step down, and it steps down in specified increments as the part builds up. So you can see in this picture, this is simply just a single extruder design. It only has one nozzle, and you're printing with just one material. And these supports are also the same material that the part is printed out of. Also, we have dual extrusion type 3D printers. Some printers even have 4 or more extruders. But in this case, you can see there's the material that the part is printed out of, and then we have a dissolvable support material as well. So we'll talk a little bit more about this pretty soon in the webinar, but that's basically how it works in a nutshell, and the types of extrusion methods that are out there. Okay, support material. There's 2 types. We have dissolvable supports, which you can see up top, and then we have the support material, which is just the same as the part. So as far as dissolvable supports go, these give you more design freedom because they just dissolve away afterwards in either water or some type of solvent, depending on the material that you're printing with. On the other side, we have supports that are the same material as the part, and this kind of limits you because in your design freedom, because you have to actually remove these with a pair of needle nose pliers or a dental pick. It's very time consuming, and it can be very difficult, especially if you have small internal passages or confined spaces. It can be almost impossible to get that support out. So that's where you have the big benefit of dissolvable supports. If you are working with dissolvable supports, you have a lot of design freedom. It reduces post-processing costs. And if you're dealing with supports that are the same as the printed material, you'll probably want to minimize the amount of supports that you'll need as much as possible, and we'll talk about that in the next few slides. So as far as the thinking goes for designing for 3D printing, you really need to think outside the box. It's totally different than designing parts that will be machined on a mill or a lathe. And you also have to think about the design complexity paradox, which is basically an idea that adding complexity to the part doesn't make it cost more. And in some cases it can actually reduce the cost of the part. So it's kind of counterintuitive to the way you would normally think to design a part. So you can see the pictures on the screen. Even though they're printed in metal, which some FDM printers can do, desktop metal is doing that. But they're just meant to give you an idea of some of the things that you can do, and different ways of thinking. It's printing a part that was designed for machining on a mill isn't the best way to go for 3D printing. That's not really where 3D printing shines. And you can see here you can do mesh and lattice structures, so that's something to think about as well. You have large degrees of design freedom. You can also take advantage of topology optimization software that's out there, and generative design, which is also great for 3D printing as well. So another thing to keep in mind when you're designing your parts is the height of the part in its orientation that it's going to print in. So the printer has a specified layer height, and your part needs to be divisible. The height of your part should be divisible by the layer height to ensure that you have an accurate part. So I have two examples here on this slide. You can see the first example, the part is 16 millimeters tall, and we have a layer height of 0.1 millimeters, and that gives us 160 layers. So that's okay. The printer will only print in one specified layer thickness. So if we move on to the second example, we have a part that's 56.58 millimeters tall, and we have the same 0.1 millimeter layer thickness, and that gives us 565.8 layers. And here's the problem: you can't have 0.8 of a layer, because the build platform will only step down 0.1 millimeters every time. So it's going to print 565 layers. So your part's going to come up a little bit short. Okay. Adding radius to corners and adding fillets. So you're probably not new to adding fillets to corners or around the edge of features. You can see in this top picture there's no fillets, and fillets added here. That just adds strength. Pretty common practice in most designing. And then the big takeaway from this slide is adding radiuses to corners. So you want to stay away from parts that have sharp corners. You can kind of think of it like designing a part for milling. If you're going to mill an internal cavity, you're not going to have perfectly square corners. You just can't do it with a round bit. So you're going to design radiuses on those corners commensurate to the bit size that you plan on doing. It's it's faster that way. You save money. It's just the way to do it. So for 3D printing, it's kind of similar, but if you have a sharp corner, basically the print head is moving along and it has to come to a complete stop very abruptly and then change directions and then start going again. And it can't do that perfectly, so it's going to overshoot the corner a little bit, correct, and then head off in the other direction. So this will cause bulging on the corners, and you'll notice you can actually see and feel the corners bulge out a little bit because of this run over past the end of the part. So to avoid that, all you have to do is put a radius on the corner or a fillet, and that way the print head, as it travels along, all it has to do is slow down a little bit as it makes the turn, and then it can go off into the new direction at just about the same speed. So that will reduce the issue of the print head overshooting the corner, and your parts will come out without bulged corners. You'll have a nice tangential curve on your part. Alright, probably touched on this before in the previous slide, but just to talk about it again, removing excess material. If you don't need the material there for one reason or another, get rid of it, because it's going to save you a lot of money and possibly print time as well. And print time is money, so the more efficient you can allow the printer to print the part, the less material you have, the less support material that you need to print the part, the more time and money you're going to save. So again, this is these parts were printed on a DMLS printer, but it still illustrates the concept. So on the left here we see a legacy part. Looks like a tube with brackets welded to it. Printing this alone would be very inefficient and not the best use of additive manufacturing's capabilities and what it's really useful for. So they probably use some type of generative design software to create these iterations of it. And you can see how much material was removed and how different it looks. And this is really the direction that design needs to go for 3D printing. It saves, like I said before, saves on material, saves a ton of weight, and overall it's way better than printing a legacy part like this. It just doesn't make sense to do. Alright, avoiding unnecessary supports. So basically 45 degrees of overhang is pretty much your limit until you're going to need support under the overhang. Basically what you want to do is design self-sustaining geometry into your parts, and what I mean by that is allowing each layer to build on top of itself, or build on top of each other. You never want to have, or you want to avoid material that overhangs, because you can't just print in mid-air. You need something underneath it so the printer has something to print on. So you see 60 degrees isn't too bad. Pretty much any printer can handle that. 45 degrees, it gets steeper, but still within the capabilities of pretty much all FDM printers. And then once we get past 45 and get to 30, it gets pretty steep and you need support material. So that's what this is. You can see the support material underneath it. If you have dissolvable supports, again, not that big of a deal. The dissolvable support material does cost money, so you are adding cost and complexity to the part, but if that's what you have to do and you can't design around it, it is what it is. Also, I want to touch on an idea here regarding internal passages or holes. Normally, internal passages and parts or holes are round because when you design it, it's going to be machined and drilled with a drill bit, and drill bits are round, but we don't have those limitations in 3D printing. So what we can do is make a square hole. Turn the square on end, you get self-sustaining angles, 45-degree angle, and you won't need support material. So the great thing about that is you don't have to get in here and clean out all of that support material. Unlike the hole, that would have to be supported because you have a pretty substantial overhang here at the top of the hole, and you can only reach back there so far. If it goes all the way through into the middle of the part, you won't be able to get all that support material out. So that's something to think about as well. Yep, already talked about using self-sustaining geometry. Try to use self-sustaining geometry when you're designing the entire part, not just a portion of it. Try to get the entire part to print without support material. That's kind of the goal. That's the most efficient way to do it. Bridges, just something to keep in mind. A bridge is basically a layer of material that is stretched between two features. So most printers can do short bridges between two features, but you want to minimize bridges as much as possible, keep them as short as possible. So you can see in the picture down here, the shortest bridge isn't too bad, but as they get longer you can see the material starts to sag in between the features that the bridge is bridging across. So we want to avoid that as much as possible. Normally you need supports to print these larger bridges, but just so you're aware, you can bridge between two features as long as they're not too far apart. Longer bridges you want to stay away from, or just realize that they're going to need a substantial amount of support material to support that bridge. Alright, Z-axis holes and perimeters, depending on the printer. So this is good. It's good to know what type of printer you're working with and what it's capable of. Some printers will compensate for this. Some have settings where you can set it to compensate for it. But basically what this is talking about, the nozzle of the printer is extruding basically a cylindrical piece of material out of a round nozzle. But the nozzle is going to compress each layer a little bit. So instead of a round layer of material, you're left with something with a cross section that's more elliptical. So in the software, whatever pre-processing or slicer you're using, it thinks of it as this round cross section. So if this is a hole, you can see your center line on the hole. So this is what's going on in the slicer, but when your software. But once the part is printed, this is actually what's going on. So you can see the layers compressed, and it kind of it gets wider. It oozes out a little bit. So the diameter of this hole is going to be smaller. And that's something to take into consideration for sure, because If you don't compensate for this, you're going to have a lot of issues with the fitment of parts. One thing that you can do, like I said, you can compensate for it in the slicer that you're using. Some have that option, or you can compensate for it in your CAD software when you're designing for it. And sometimes you can have dimensional issues for the same reason. On the outside of your part, any dimension can be affected by this if not taken into account. So definitely something to take into consideration when you're designing for additive manufacturing is the part strength and layer orientation. So this is a huge thing to take into consideration. You can think of a part that comes off an FDM printer as kind of like a piece of wood. It almost has a grain to it in terms of the layers. So the layers will bond to each other, but it won't be nearly as strong as a solid plastic part, as an injection molded part. So if we look at the pictures here, just to illustrate this, we have a picture where the part was printed with horizontal layers, and we have a tension load applied to the part with these arrows. So it's basically pulling apart these layers. So in this orientation, they'll have it's likely that they'll delaminate. But if we go over here with the layers are in the same orientation, we have a bending load applied, and the layers are very strong in this orientation because we don't have a tension force that's pulling the layers apart, it's compressing them. So generally FDM parts are very strong in compression, but weak in tension, generally, depending on your layer orientation. So that's something that should be taken into account for sure. Then we have a tension load applied in the other direction. You can see it's kind of pulling on the layers, axially, I guess you could call it, or along the layers. And the part is also very strong in this orientation. And again, we have a bending load applied, but the layers are in a vertical orientation this time, and you can see that if it was bent, it would be very easy for this part to crack right along one of these layers, because the layers are always the weak spot in an FDM part. If you're ever in doubt of how you need to design a part or what kind of parameters you need to design around, because each printer is a little bit different, I would highly recommend consulting the printer manufacturer's manual, because they will have the actual design specifications and the capabilities of that printer. And that pretty much concludes the webinar. So again, if you have any questions, you got my email on that slide. Feel free to send me an email. Also, this video will be posted on YouTube, Facebook. It'll be on our website, trivectorprinting.com, so you can always leave a comment there. I do my best to respond to everyone's comments. Follow us on social media. Right now we're doing a lot of on-demand 3D printing for our clients, but in the background we're also doing some development on new materials for FDM printing, so that's something to keep an eye on in the near future, probably early next year. you'll hear more about that. So thanks for watching the seminar, and hope to see you again.